Welcome to my channel. Right, that's some questions that were sent to me to attempt. All right, so I'm just going to briefly show us the question. Right, so we dive straight into these questions. The questions that need me to calculate, I'm going to calculate it, and those questions that just need explanation, I will just explain them. Right, question one: express the work energy theory mathematically. Right, to express the work energy theory, that's W, question one, equal change in kinetic energy. W is the work done on an object. YKE is actually kinetic energy, so that's change in kinetic energy, and we all know that kinetic energy equal 1 over 2 mv square, and then we know that v actually change in distance over time. All right, so I believe I've answered the first question. All right, we can actually just insert this. Yes, it becomes 1 over 2 m dt square. All right, so that's question one. Question two says give two examples each of conservative and non-conservative force. Okay, let me just differentiate between conservative force and non-conservative force. The first differentiation I'm going to do on them, it's actually their parts. All right, conservative force is actually parts independent. Conservative force are part independent, meaning the work done by this force is independent of the parts taken by an object. Okay, so it's only depends on the initial and the final position. Why for non-conservative force, it's depends on a specific part. The work done by this force can vary depending on the routine an object takes from one point to another. Okay, concerning potential energy for conservative force, um, it's actually associated with potential energy. The work done by conservative force can be expressed as a change in potential energy, and this potential energy is a function of position. Why for non-conservative force, it's not associated with potential energy. Okay, so um, containing energy conservation for conservative force in an enclosed system where only conservative force are at play. Mechanical energy, that's kinetic energy plus potential energy, is conserved. So the total energy remains constant over time. Why for non-conservative energy? It's actually energy dispersion. So quickly, I would also now I'll go straight and answer the question. Give two examples. Okay, so two examples of conservative force from what I've discussed is number one, gravity, number two, elastic force. Why that of non-conservative energy, we can see friction, we can see air resistance, and we can see tension in a non-ideal rope. All right, question three says that we should express mathematically the principle of conservation of mechanical energy for a system involving non-conservative force. Okay, so I'm just going to just give something general. All right, the principle of conservation of mechanical energy actually states that the initial mechanical energy plus the work done by external force is equal to the final mechanical energy of the system. What I'm saying is E initial, right? E initial is actually kinetic energy plus potential energy, right? Plus work done by external non-conservative on the system. So it's all right, external. Yeah, this is where the non-conservative comes in. Then we have the mechanical energy, the final from what has been stated. So this does Ke plus Pe. Right, the conservation of mechanical energy holds true for the system where only conservative force like gravity are involved. Now, for non-conservative force, so when non-conservative force are present, the work done by this force needs to be considered in the equation. This one. Right. So that question has been answered. Um, we'll move to question 4. Right, this question 4. So let's dig in to what we need. Right. So if you look at from where we've been solving, you discover that it's kind of something progressive. Right. So we will just solve it straight away. Right. So what we have is I would just write W. That's the work done by like every work done. It's equal to change in the mechanical energy. Right now, let's discuss about this. So the first thing we're going to talk about is the work done, the applied force, work done by the applied force, work done by the right. So let's talk about the work done applied. That's I'm talking about this one here. So the force there is 100 Newton times the distance is 1.50 meter, and this should give us 150 joules. So I've talked about the work done apply. So the next thing I'm going to talk about is the work done by friction. This friction here, this one here. Right, the work done by friction, WF equal minus 2.5 times 1.50 equal minus that's negative 3.75 joule. All right, the reason for the negative sign, we should know that then these are vectors quantity, so it's very very important we show the direction. So the negative sign is actually trying to say it's opposing the motion of the object there. All right, so there's still one more energy that we've not explained, and that's the initial kinetic energy. Right, so the initial kinetic energy to be 1 over 2 mv square. In the question, we're told that the I'm sorry, I omitted the formula of the kinetic energy is as equal half mv square. So the mass in the question is 50 kg, while the velocity in the question is 1.0 meter per second. So it means that the initial kinetic energy is 25 joules. Okay, so W, that's the weight and the normal. Right, the weight and normal of the force will just be weight W equal mg, and then we're told that g is 9.8, so it will just be 50 times 9.8, give us the answer. Normally the normal is actually in the opposite direction to the weight, so it's will just be having the negative sign. All right, so this the net force for the work done. So all we just need to do is to add this value, this and this together. We're going to get um, the network of the question. All right, let's move to the next thing. All right, question 6. How are we going to solve that question? Now, to find the maximum compression of the spring, we can use the conservation of mechanical energy. That's the initial kinetic energy of the mass is converted into potential energy stored in the spring when it reaches its maximum compression. Okay, so the potential energy stored in the spring, I'm going to call it PES. Right, so our PES, and then it will be equal to 1 over 2 kx squared, where k is the spring constant and where x is the compression of the spring. So now the initial kinetic energy of the mass is given by, so k e equal 1 over 2 m, the initial velocity square. So the question actually asks us to find the maximum compression of the spring. So for us to get the maximum compression, it means that the potential energy equal to the kinetic energy. So we'll be having our equation as 1 over 2 kx square equal 1 over 2 mvi square. So putting in the value from the question, we have 1 over 2 times 10 uh, times 7 square. That's for this one. Equal 1 over 2. The spring constant is 5,000 times x squared. So 1 over 2, we take 1 over 2. 0 here, we eliminate one of the 0 here. So it means that, I'm sorry, it means that x squared equal 49 over 500, which gives us 0.098. Now taking the square root of both sides, implies that x equals 0.31 meter. So that's the maximum compression of the spring, 0.31 meter. All right, question 7 says define linear momentum mathematically. All right, linear momentum, let's say P is mathematically defined as the product of the object mass, let's say m, times the velocity. So this settles it. For more explanation, you can look at my previous video on momentum, impulse, and impact. Right, question 8 says define impulse mathematically, and is it a vector or a scalar quantity? Right, it's also in my previous video. You can place the search on it to actually save time. Right, question 9. How long will an average braking force of 2000 Newton take to stop a 2000 kg car traveling with an initial velocity of 10 meter per second? All right, so let's just take in our parameters there. We have force F, the braking force, equal 2000 Newton, and then we have the mass of the car, which equal 2000 kg, and then we have the initial velocity, vi equal 10 meter per second. All right, so we are asked to find the time. T is unknown. All right, the best equation to use is the equation of motion. This says vf, final velocity, equal initial velocity plus at. So straight away I'm going to make t subject to formula. T equal vf minus vi over a. This comes here, and then we divide both sides by a. That's how we got this formula. All right, since it's coming to rest, and when we're talking about motion now, when a body comes to rest, it means final velocity is equal to 0 meter per second. When a body starts from rest, it means initial velocity is equal to 0 meter per second. All right, so now, but in this question we're talking about braking, so it means that it comes to rest. It means vf equals 0 meter per second. All right, so it means t equal minus 10 over a. Now the question is, what's a? We know from Newton's second law of motion that F equal ma. For the variable side by m, we'll discover that a equal F over m. And in the question we have F to be 2000 Newton, and then the mass 2 kg. So it means the acceleration is actually 1 meter per second square. Now substitute the value in this, it now becomes minus 10 over 1 equals minus 10 seconds. So it will take 10 seconds. The minus is actually telling us that there's a retardation, like the time is actually reducing. So the minus sign is actually telling us there's a retardation, it's coming to rest. All right, so we'll move to the next question. Right, next question says, states the principle of conservation of linear momentum. Okay, the principle of conservation of linear momentum states that the total linear momentum of a closed system remains constant if no external force acts on it. In other words, in the absence of external force, the total momentum of a system of objects before an event like collision, definitely, or explosion, is equal to the total momentum after the event. So mathematically, it will be initial total momentum equal final total momentum. For more explanation and a breakdown on this, look at my video on impulse, impact, and linear momentum. Right, the next question says, what is the difference between elastic and inelastic collision? All right, I'll start from kinetic energy of conservation. I'll use it to separate, differentiate them. In an elastic collision, kinetic energy is conserved. This means that the total kinetic energy of the system before collision is equal to the total kinetic energy after the collision. Why for inelastic collision? Kinetic energy is not conserved. Okay, so it just means that kinetic energy is actually transformed to another form of energy, such as internal energy or deformation energy. All right. Let's talk about the nature of collision. For inelastic collision, the nature is such that it bounces off each other with no loss of kinetic energy. Why that of uh, inelastic collision? They stick together after collision, and then this actually causes deformation upon the impact, and then it results into loss of kinetic energy. Now let's talk about the coefficient of restitution. For inelastic, it's equal to 1, and that means indicates perfect inelastic collision. Why not of inelastic collision? It's less than 1, which indicates a less than perfectly inelastic collision. For the proof of this, just check my initial video. Okay, so let's move to question 12. That's a calculation question in question 13, right? So question 12 is actually talking about um, the principle of conservation of linear momentum. So let's spell out our values and calculate it. All right. 0.005 kg bullet. Mass of the bullet equals 0.005 kg. It is fired horizontally at a 100 kg block of metal. So I will write down the mass of the metal to be 100 kg. Okay, which is at rest. So it means that the initial velocity for the mass is 0 meter per second, and then it sticks in it. So it means that we actually have equal velocity. That's an inelastic collision. Okay, let's find out the speed. All right, the speed is 0.25. It means v equals 0.25 meter per second. After impact, we're asked to find the initial velocity of the bullet. We don't know the initial velocity of the bullet. Right, so our conservation of energy will be, for an inelastic collision, will be mb ub plus mm um equal mb plus mm a times v. All right, so this, I'll substitute the value. All right, I don't want this to exceed 30 minutes. Okay, so I'll just quickly explain. I just substituted the value. We spelled out the value here. So I just substituted the value, and the initial um, velocity for the metal is actually 0, because it was stated that it was at rest. And since they stick together, they share the same velocity after collision. So, and this plus this actually arrived at this times 0.25, which is the velocity after collision, gave us this. So dividing both sides by the coefficient of ub, so it means that the initial velocity for the bullet is 5000.25 meter per second. All right, to the last question. All right, a bullet of 0. So I'll just write mass of bullet 0.015 kg. Okay, moves at a speed, that should be the initial speed, 300 meter per second, pass through a 0.02 meter thick. Okay, so let us say thickness as a 0.002 meter thickness of foam sheet and emerged with a velocity with a speed of 90 meter. So there's a reduction in the speed. So final speed would be, sorry, 90 meter per second. Okay. Assuming the speed changes uniformly, that statement is very important. Calculate the average force that's impendent on the motion. Okay, so we to calculate the average force. All right, let's dive into the question now. Um, okay, F average, the average force. Since it changes uniformly, we'll be using change in P over change in C. All right, so let's take them one after the other. Let's talk about change in P. That's momentum, which will be M times change in velocity. That will be 0.015. Change in velocity will be 90. That is initial velocity minus, sorry, final velocity minus the initial velocity. So this should give us, right, the reason why we have a negative value, it's because the final velocity is actually less than the initial velocity. All right, so now let's talk about the time, the change in time. Now the change in time will be the distance over average velocity, average velocity. Okay, so let's talk about the average velocity. How do we get the average velocity? Average velocity will be gotten as let me see, initial velocity plus final velocity over 2. That will be 300 plus 90 over 2. 300 plus 90 over 2 will be 195 meter per second. Now back to this formula. The distance now will be the thickness, which will be 0.002 meter over 195 meter per second. Right, so this will be the time taken. So now we'll put everything back to our force, our average force. We've gotten the momentum, the change in momentum. So that's right, average equal the P over the T minus 3.15 over 1.026 times 10 raised to the minus 5. Right, so after calculating and simplifying it, we have minus 0.307125 Newton as the average force that impeded the motion of the bullets through the sheet. So definitely, it's will definitely be opposing the initial force that was sent, like the bullets passing through it. The first thing we discover was that there is change in velocity. The velocity will reduce the impact. The thickness of the foam will now determine how much speed will be excited inside of it, and then automatically the force will actually be having that negative sign. So that's the end of part one of the question that was asked. um Please subscribe and then click the notification bell to get notified when the second part of the question will be solved. Thank you.